Hello, welcome to your lesson on logarithmic functions. This is kind of a part 2 video. Make sure you've seen the video that introduces logarithms first. Okay, logarithms, big idea in mathematics. We talked about this definition of a log in the last video. Basically, it tells us how to change an exponential equation or function into a logarithmic one. The rule basically works like this. If you have a log base 5 of something equals something, change the exponential form, this base of the log becomes the base of the exponent. That number here becomes the exponent, and that is what it's equal to. We know this equation makes sense. Here's what it looks like in log form. Okay, with that, let's see if you can figure out a couple additional properties based on that basic rule of logarithms. So let's say you have this. What should that equal? Well, in your head, you should be thinking, well, a to some power, because that's what this tells us, there's an unknown value here, a to some power, whatever that number is, must equal 1. All right, well, it must be 0, because a to the 0 power is 1. Try the same thing here. What does this equal? Okay, this time you're thinking a to some power over here equals this value, a. Well, the only way to get this to be equal to that is if that power is 1. Again, a to the first power equals a. Okay, how about you try it down here? This time you're thinking a to some power equals a to the x. Well, to get these to be equal to each other, this exponent must be an x, therefore that equals x. A to the x equals a to the x. These are additional properties of logs you should be aware of. Okay, so now we're going to do a little bit of a investigation. We're going to look at what is the relationship between an exponential function and a log function, and they both notice have the same base. So as this exponential function has a base, and so does this log one. So what's the relationship there? Well, we can't exactly graph something with an unknown base, so we're going to say, okay, well, let's use a common base. And like I said before, a common base is 10. So we're going to graph 10 to the x, which is like our a to the x, and log base 10 to the x, which is using the same base in the log. So we're going to graph these two and see if we can notice any relationships. Let's go to Desmos now. Okay, so here I am. I have, here's our log graph. So that you know, a log graph looks like that. We'll talk about those details in a moment. Now I'm going to graph y equals 10 to the x. So now I have that one here. Okay, and do you see any relationship here now? Now I'm going to throw something else in here for you. I'm going to throw in the line y equals x. You may be remembering that. Oh, when did we use the line y equals x? What was that topic we were talking about? All right, well, hopefully jog your memory now. When you have the line y equals x and you have functions that are reflections of one another across that diagonal line, which these are definitely reflections of one another, well, then those two functions must be inverses of one another. So that's what we're looking for here. Logs, this log equation and this exponential one are inverses of one another. So let's continue here. So questions, what does the orientation of the functions in relation to the line y equals x tell you? Well, again, they were like mirror images across that line, therefore they are inverses. What is the domain and range of each function? And how are those related? Well, let's take a look. What's the domain and range of this one, the log graph? No, let's actually begin with the green one, the exponential. Okay, and now what's the domain and range of this one, the log graph? Okay, well, hopefully you saw that the domain and range are kind of like interchangeable. The domain of the exponential becomes the range of the log graph, and the range of the exponential becomes the domain of this one. And that's what happens when we have inverse functions. We're basically swapping x and y values, so the domain is all the x values. They become the y values, or the range of the other one, back and forth. Okay, so let's take a look at some more things. So generalize the relationship then. Based on what we just talked about, how can you generalize this relationship? And let's look at it now. So there we have it. If we have a function, which is an exponential, then its inverse, remember this is a symbol for inverse, its inverse is the log graph with the same base. And that's what we just saw. These are inverses, so this is the actual statement that shows us that. Okay, that's an important thing to know about log graphs and exponentials. Let's look at it in using a different one. Let's use another common base of 2. So here's y equals 2 to the power x, exponential function. Fill in some of these values. Let's have you fill in the first 3 here. Or let's say the first 4. Okay, let's check. That one is 1/4, because when you put a -2 here, then you end up with 1 over 2 squared, which is 1/4. All right, next one, 1/2, because you put a -1 here, that becomes 1 over 2 to the 1, which is 1/2. Put a 0 there, you get 1. Put a 0.5 there, which means a half. That gives you the root of 2, which works out to 1.41. If you continue like that, 2 to the first power is 2. 2 to the 1.5 power is the same as 2 to the 3 over 2, which gives you this, and it equals that. And 2 to the 2 is 4. Great. Then let's try the same thing with a logarithmic function. So we have this log function here. Now, using what you know about logs, you should be able to do this. So if you put a 0 in here, you're thinking in your head 2 to some power equals 0. All right. So again, I wrote that here. 2 to some power equals that value, right? So 2 to some power equals 0. And that power does not exist. You cannot have 2 to some power equaling 0. It's impossible. How about the next one? 0.5. So put 0.5 in there. 2 to some power equals 0.5. Well, it's -1 because 0.5 is like a half. So 2 to the -1 power equals 1/2. Next 2, we have 0 and 0.58. 0 because 2 to some power equals 1. Well, the only way to get that is 2 to the 0 power. And then this one you would need a calculator probably. Next one, next one, next one. Why are we doing this? Because again, we already established that these will be inverses. So I did the exponential function, now I'm doing the log function, and let's see what happens. When we graph those two, here's the exponential, y to the power 2x. Here is the log function, and we could plot those point by point. If I took those points we just found, we could plot them point by point and get those graphs. We notice they are inverses across that, so we're just reinforcing the idea of inverses, right? This one and this one are inverses of one another. Okay, let's take some notes. So here is a summary of what we've just looked at. So take a look, pause the video, read this on your own here. We see a graph of a log in that graph, and let's fill in the blanks here. First one, the log graph. The curve crosses the, which axis does this log graph pass through, and at what point does it pass through? Okay, that answer is it crosses the x-axis and it crosses at the point 1, 0. As you may remember, exponential graph always passes through the point 0, 1. So now since it's an inverse, it's 1, 0. All right, so again, this is 0, 1, and this is 1, 0. Also, x equals 0 is the asymptote of the log graph because for the exponential, the asymptote was y equals 0. And now we have the inverse, so now the logarithmic one has an asymptote going up and down right here, x equals 0. Okay, next, the domain. Okay, remember what the domain is for an exponential? Well, what's the domain for a log graph? Well, it's all positive real numbers. The log graph will go forever this way, and it will go forever this way. The domain is all positive real numbers. Not forever this way, sorry. There's an asymptote here at x equals 0, so the log graph gets forever closer to that asymptote but never passes it. So that's why it says all positive real numbers, because x values must be greater than 0 to be part of this domain. What about the range for the log graph? Well, the range is all real numbers. So it goes from -infinity here for y and goes up forever to positive infinity for y. So range is everything. And remember that these are the inverses of the domain and range of the exponential. The exponential had a domain of real numbers, and now the log has a range of all real numbers. And then again, the exponential had a range of values greater than 0, and now the log graph has a domain of values greater than 0. So remember that inverse relationship there. Okay, so we've been talking about exponential growth and logarithmic growth. It's important to understand these graphs now. Let's just summarize again. When you graph a log function, there's a basic log function. This would have a base 10. It passes through point 1, 0. It has an asymptote right there at x equals 0, vertical asymptote. And I want you to now answer these two questions. Why is 1, 0 point on this graph of y equals log x? Well, I hope you saw that, because if you put in x value of 1 here, you're thinking 10 to what power creates a 1, and the only answer is that this must equal 0, 10 to the 0 power, and that's why we have a 0 there. And why can x values not be less than 0? So think about that. If you put a negative number in here, you're thinking 10 to some power gives you a negative number. That's impossible. It will always be a positive number when you have 10 to some power, even if you have a negative power. Okay, a couple key points you should be aware of on the log graph are these two here. 1, 0 we already talked about, but you should also know there's a point like this. In this case, we have the graph of log base 2 of x, so a point 21 is on there. So the second key point on the log graph is always a1, a being the base. So the base number and 1. And why does that work? Because again, if you put a value of 2 in here, then we would say 2 to the first power is equal to 2. So that means the answer to this y value must be 1. So we have that there. Think about that for a moment, how that works. Okay, try this problem here. All right, in A, we have translation 2 units to the right, and then translation 1 unit up vertically, right? So you should know that from our transformations. Write down equation of the asymptote. Well, to do that, it could help to look at the basic log graph. Here's the basic log graph, and in our case, there's the asymptote of a basic log graph. In our case, we're moving it 2 units to the right. So imagine all this moving to the right. So now the asymptote will be here, right? And the graph will kind of come to that asymptote. So that asymptote is now at x equals 2. So that shift, horizontal shift, tells us where the asymptote moved to. Remember, with exponential graphs, it was the vertical shift that moved the asymptote, but in this case, the asymptote moves left to right like this. Okay, find the domain and range of the new function. Well, here they are. Domain is all x values greater than 2, and the range is all possible values. And we know that because, again, here's our graph after it's been shifted like this, and there's an asymptote here. So again, domain is 2 and greater, and the range is all values. Okay, last question. You're trying to sketch the inverse, so you put the y equals x line, and you can then draw the inverse function here. You can draw the inverse by picking key points from here and then inverting them. For example, the point 3, 1, is that a point on there? Maybe, will become 1, 3 on here, and so on and so on. Okay, let's talk about inverses some more. Since logs are inverses, let's remember how to do inverses. Try to find the inverse of this, see if you can remind yourself. Okay, so here are the steps. To find the inverse, we swap the x and y values, and then we go ahead and solve it for y. So that was the inverse there. How about this one? Okay, swap the x and y values right here, and then solve for y. So multiply by 5, and then we're going to add 3 divided by 4. Okay, so that's inverses. So now let's think about inverses in terms of logs, right? So this basic one again, here's a basic inverse one. Swap the x and y, solve, 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 you get that. But what about this one? How would you get the inverse of that? Well, follow the same process. The inverse, you would swap the x and y values. And now this, you cannot solve for y unless maybe you change it to log form. So let's try. This is a base 2 in this exponent, so we're going to write log base 2 of x equals the exponent equals y. So we have taken this exponential and changed it to log form, and that is the inverse. So now we see this exponential and this log are inverses of one another, and we're just basically confirming algebraically here what we already saw in the graphs. We saw that these are inverses. Try the last one. Okay, here we go. And that, write it in that form, swap the x and y. Now write it in exponential form to the x, and we've just confirmed this back and forwards right here. Important idea, make sure you understand that. Try a few more here. Find the inverse of each. Check your work. So I'm rushing through this now, and there's actually something you may have not seen here, but log ln means log base e. So think about that one, but we'll come back to that soon if this is a little tricky for you. And try these as well. Check your work. And yeah, double check you got it all right. Again, we have e here, so we see the ln. Don't worry about that so much yet. Few more if you want.